Hello, everybody. Welcome to the Henstitute. In this particular edition, we're going to kind of look at an object on an incline. We've been doing everything on flat surfaces. We've never really looked at an object on an incline. And because of that, we're going to draw a free body diagram to start off with. So I'm going to do my normal stuff. The first one is I just have this box. So this is some kind of box with a certain mass here, and it's sitting on an incline with a certain angle. And the first one that I always do is the force of gravity. So the force of gravity is going to try to pull this box straight down like this. So there's my force of gravity. Draw it with green. The next one that we're always used to is this idea of a normal force. But a normal force means it's got to be perpendicular to this surface. So if the surface is like this, the normal force is going to be pointed upward in this direction. It's my normal force. Now I'm just drawing these a certain length right now because I don't know how long to make them, but I just have that situation going on. The other thing is, let's assume that this box stays on this incline, so it does not move anywhere. It's staying in place. Or as you put it at this angle, it just starts to slide down the incline. So it's either staying in place or it's starting down the incline. There would be one other force acting on this thing, and that would be friction. And since it's trying to slide down the incline, so since it's trying to slide in this direction, friction would have to oppose that, and friction is always parallel to your surface, so it would actually be acting up the incline. There would be my friction force. So very simply, these are the three forces acting on it. However, we don't usually stop there because it's not easy to actually use the weight and the normal force and the friction force in this fashion. For example, if I wanted to actually calculate the friction force, we know it's the coefficient of friction times the normal force, but I don't know how to find that normal force right now. So the question is, how do I find that normal force? It's not equal to the weight in this case. So it is not equal to mu times mg. That is not going to be the case. So we've got to do something a little bit different. So here's the common thing to do when you're on an incline, is to actually take that force of gravity and split it up into two components. One of the components is going to act perpendicular to the surface. So in other words, the force of gravity is holding it onto the surface itself. This I'm going to call F perpendicular. So I'm going to put a little perpendicular symbol underneath it. The other thing it's trying to do is actually pull this down the incline. So a portion of this weight, this force of gravity, is trying to pull it down the incline. I'm going to call that force, and I'm going to use the parallel symbol. So the cool part about this is, even though the normal force, or the force of gravity is on there, and we know that the force of gravity is equal to the mass of the object times gravity, what we often do is we split this up into its two components. It's going to have a component that's going to be perpendicular to the surface and a component that is parallel to the surface. So if I make a little triangle out of all three of those, I'm going to draw it down here. Here's the perpendicular force, just making it a little bigger for you. You would add to it, since these are components, you would basically put it down here. The parallel force I'm going to put up here. Together, they are going to form the force of gravity. So the force of gravity is going to be the hypotenuse of this system, or this system of forces, because this is where their right triangle would be. So the question is, how is that going to be related to everything? Well, here's the really cool part. If you imagine that this object started out flat, in other words, let's say this was flat, force of gravity is straight down. So the force of gravity and the force perpendicular are equal to each other. But as I tilt this up a certain angle, in other words, I make this a little bit steeper like this, now the force of gravity is still acting straight down, but the perpendicular force is this. So here's the cool part. The amount that you tilted this up, this angle that you tilted it up, that's how much the force of gravity moves away from this. So this angle up here is actually equal to that. So what that is telling me is this angle right here is theta. It's the same as the angle of the incline. So now I have a way of relating these two. Since the perpendicular force is adjacent to it, that's cosine. So the cosine of theta would equal my perpendicular force over the force of gravity. So my perpendicular force would be equal to the force of gravity times the cosine of my angle. Or we commonly write mass times gravity, so the acceleration of gravity times the cosine of theta. All three of them multiplied. Parallel force, since it's opposite my angle, it's sine, and we have the hypotenuse, so here it's going to be the force of gravity times the sine of the angle of the incline, or in other words, it's going to be mg times the sine of my angle. And then I have ways of actually relating everything. So for example, if this box is sitting here on this incline, and these are the only forces acting on it, this blue, red, and green, the perpendicular force would be equal to the normal force because, think about it, normal force means perpendicular. So these would be equal to each other. The other thing we would have is we would have some kind of friction force. Now, the parallel force, the force of gravity pulling it down, if this box moves at constant velocity down the incline, or it doesn't move at all, then they're equal to each other. So they could potentially equal the force of friction if it moves at constant velocity, so velocity is constant, or velocity is equal to 0. However, what we would have if this thing did slide down or up the incline in some fashion, then I would have a difference between these would be equal to my acceleration. So if this thing was actually accelerating down the incline, so acceleration down incline, then what I would have is my parallel force would be down the incline. It would actually be greater than my friction force, and those two would equal, actually change this to a completely different color, the mass of the object times acceleration. This would be Newton's second law, F, this would be the net force down the incline, would equal m times a. So this is what's happening. So really the reason why they're equal up here is because I have no acceleration. The key idea I want you to get out of this is these two little statements right here. We typically do stuff with that and then maybe borrow this to try to calculate what the friction force is, and we're going to use this a little bit in our lab coming up. So hope you enjoyed this little edition of the Henstitute with objects on an incline.